let us talk about the second half of this lecture. Here I want to talk about 3 pieces of advices when you are building your machine learning model. The first piece of advice is called the Occam's razor. This best explanation of Occam's razor is the following statement by Albert Einstein. An explanation of the data should be made as simple as possible, but no simpler. If you read the textbook, chapter 5, it says that the simplest model that fits the data is also the most plausible model. So in order to explain this Occam's razor, let me try to explain why simpler usually means better. There are 2 notions of complexity. One is the complexity of your hypothesis set, and this is the VC dimension. The other one is the complexity of your hypothesis, and this has to do with your regularization. And a complex h, small h, usually implies a more complex hypothesis set. For example, you can consider using a quadratic equation versus a linear equation. And if a model is simple, then usually you will have a simple h as well as you will have a simple hypothesis set. So why is simple means better? If you have a complex hypothesis, then certainly you can shatter a larger set of data points. But this may not mean anything. Okay, because what is more useful is that if you can shatter the same set of data points using a simpler hypothesis, this actually means more. Think about that. You are using a 50th order polynomial, and then you're trying to shatter a set of data points, and because you have a 50th order polynomial, and certainly you can shatter a much larger data set. But if your second order polynomial can also shatter the same set of data points, then certainly your second order polynomial is a more powerful and more meaningful classifier than a 50th order polynomial. And this notion is hand-waving. I want to emphasize that. It's not mathematical. It just gives you a overall reasoning why simpler usually means better. I want to also convince you that when you try to fit your data sets using your model, and if you fit very well using the model that you are proposing, you should not feel happy too immediately until you have tested the performance. And here is what I call the problem of who has more scientific evidence problem. And I want to claim that having a fit really does not mean anything. Here you have 3 scientists, A, B, and C, and then you have scientist A looking at 2 data points, and then the person would say that I am going to fit these 2 data points using a straight line. Versus scientist B says that I have 3 data points, and then I'm going to fit these 3 data points using a line. Now compare A and B, you may certainly say that scientist B has more evidence because he or she has 3 data points. But if you look at scientist C, you see that the person actually chooses to fit these 2 data points in the presence of an outlier. Okay, and therefore which one comparing between A, B, and C has more evidence? It's actually C. Why? It's because because it has a data point that can falsify the hypothesis that you're using. So if tomorrow this data point is no longer living here, but let's say the data point is living there, then certainly the hypothesis that he's going to use will change to this line. And this is the power of the model that scientist C will have compared to scientist A and B. Scientist A can only consider 2 points, which does not have the third point to verify. Scientist B says that I will only fit into these 3 data points, and I'm assuming that these 3 data points, they're living on the same line, and they're perfectly fine. There's no noise. And therefore, having a fit in the A case, having a fit in the B case, makes you feel very happy because you can fit the data very well. But in terms of the testing, in terms of generalization, then only C has the most evidence to be true. Let me also try to convince you that having a fit is really not the point of machine learning. Suppose that someone sends you a letter saying that I predict that the winner of a game will be this team. And then if you read the letter and you watch the team and you watch the game and it was correct. And then the person sends you a letter 1 week later and then predicting the next game, and you watch the second game and it is also correct. And so you're very happy because you read the letter and then the person says this team will win, and then you read a week later, you read the letter, this team won again. And so you feel very happy. And then this has been repeated for 5 weeks. So if you're a big fan of the Purdue basketball team, if someone says that Purdue basketball team will win this weekend, and then a week later, you get another letter that says that Purdue basketball team will win this weekend as well, and both of the weeks are correct. And this has been repeated for 5 weeks. And then finally, you receive a letter, and then the letter says that pay me a check of $50 if you want to get to the next prediction. Okay, because you have already seen 5 correct predictions over the past 5 weeks, should you trust this prediction for the next game? Now, if you try to frame this problem into the machine learning setting, you will feel that, yes, I'm fitting very, very well to the past events, and should I really trust what will happen in the future? And this is the problem of testing or generalization. And so what's happening in this simple example is the following. Suppose that you have 5 persons in this world. And suppose that you send a letter telling the 4 people that Purdue basketball team will win, and then you tell the rest, the other 4 people that Purdue basketball team will lose. Okay, so imagine that you really have 8 people. You just send 8 letters to these people, with half being win and half being lose. And suppose the game came out to be Purdue basketball team indeed won the game, then of course you're going to piss off these 4 people. They won't trust you anymore because it's a wrong prediction. And so you can ignore them. However, you still have 4 people that are happy about the outcome. Then the second week, you are going to send a letter to these 4 people with 2 saying that Purdue basketball will win again, and then 2 says that Purdue basketball will lose. Okay, and so then the outcome is that Purdue basketball team actually lose in that week, and so you're going to piss off these 2 persons because you say that it's gonna win, but then it lose. However, you still have 2 people who are happy about your prediction, and then the third week came. You send a letter of win to this person and lose to this person. And of course, this person is not happy if the outcome is actually winning. But you still have 1 person left. And suppose you are really this lucky person who got correct prediction every week. And then at this point, you ask, should I really pay the $50 in order to get to the 4th week prediction? And you can see that there is absolutely no way that you can win given this setup, because for every time the feeling that you have is just a hallucination. So this football game is really what we call not a football game, but a football spam. Should you pay? The prediction fits well to the data. No, because he has sent 2 to the power 5 letters to 2 to the power 5 different people, and you are just the one of those. And there you happen to be the lucky guy to get all the 5 games correct, and it really means that fitting does not mean anything. So the Occam's razor says that among all the hypotheses, we want to choose the one that is the simplest. And having a fit does not really mean anything in many learning scenarios. What you really want to do is to make sure that your model actually fits not just your data sets, however, it has the ability to be falsified when you have a new data sample that comes in and it is not seen before. Now, let me go on and give you the second piece of advice. And this advice is called the biased sampling advice. The story goes back to 1948 when Truman ran against Dewey for president election. And the Chicago Daily Tribune ran a phone interview of how people voted. And the poll says that Dewey won the game. However, on the actual election day, Truman won the election. So what could go wrong in this event? Well, you may be very puzzled because when you conduct a survey and then the survey says that one candidate is likely to win, however, on the actual day, the other person won the election. The thing that went wrong is this word, phone interview. Why? Because back in 1948, there are only very few people who have telephones. And so if you try to conduct a survey of these people, then you are not sampling well or uniformly enough within your population set. So here is what we have for the Hoeffding inequality. And there is nothing wrong with the Hoeffding inequality because the Hoeffding inequality is still predicting the in-sample error and also the out-sample error. Your epsilon is correct, your delta is correct, your in-sample distribution and also out-sample distribution, they're all fine. The only thing that is not right is that your training set is not the same as the population set. So imagine that this is your population set, and then you're going to test your machine learning algorithm on this population. Now, what you really want is that your training set is a good representative of your population set. So in other words, you're uniformly sampling from the population set to generate your training data set. However, if you're not sampling uniformly, and suppose you're really sampling in a very biased fashion, for example, you're just sampling this group of people, then certainly you will run into a problem that there is a bias in your sampling procedure. And therefore, this is a very good statement. It says that garbage in, garbage out. If you read the textbook, then you will find a statement which is very insightful. It says that if the data is sampled in a biased way, then learning will produce a similarly biased solution. Lastly, let me talk about the problem of data snooping. Consider this set of data points. You have the blue circles and you also have the red crosses. One is inside, one is outside. And suppose you have seen this data set and then you are choosing the transformation to be this. And then you can also have other choices of the transformations. And certainly which transformation is better. Now, if you see this data set, then certainly you will not choose this transform or this transform. Actually, you will choose this transform because you see the data set and you know that this is like a circle. And so once you pick this equation, you are doing a model selection mentally in your brain because you have seen the data set. Now, if you have not seen the data set, and if you just choose between these three according to your prior experience with the data, this is all fine. However, if you have actually looked at the data and then you choose the model, then this is not okay. Now, if you're only seeing the training data sets and then you are not seeing the testing data set, this is also allowed. Okay, the bad situation happens if you assume that you are seeing both the training data sets and also the testing data sets, and then from there you choose the transformation to be applied. This is what we call the data snooping. And so the comment is that it is not okay if you look at the data and then you decide, and here the data I mean that both training and also testing. Let me give you an example to illustrate the idea. Your goal is try to predict the US dollar to British pound, and then you have collected the data set D, and then for some reasons that you want to normalize so that the numbers is between maybe -1 to 1. And then you split the data into the training set and also the testing set, and then you lock the testing data set into a safe. Okay, and then you don't touch the testing data set at all, and then you try to just train on the training data set, and then you open the safe and then you test on the test data set. So far so good, every step has been properly defined, and then you get a group prediction, and then you sell your algorithm to the bank, and then you get this behavior. You are expecting to make a very, very good prediction, and then you will see some profit. However, in reality, when you test out your learning algorithm, you actually get loose. Now, what had gone wrong? Well, you have gone wrong because of a very, very subtle step called the normalization step. In this normalization step, you're normalizing both your training set and testing set together. And because of this normalization set is touching both the training and also the testing data sets, you are actually doing data snooping. You're actually allowing yourself to use information from the testing data set. So here are two comments given by the textbook. The first comment says that if you torture the data long enough, it will confess. And therefore, you need to have very, very strict discipline in handling the data. Do not see the testing data at any stage of your learning algorithm. If a data set has been affected any steps during the learning process, then its ability to assess the outcome has been compromised. So I hope that with these three practical advices, you have seen some basic principles in handling machine learning algorithms. Specifically, try to have a very strict discipline for your training and testing data set. Second, try to make sure that your training sets and also the testing set, they are equally sampled. And third, try to use a model that is as simple as possible. So finally, I want to give you some acknowledgement to the team that have been working with me really, really hard for this semester. I want to thank the College of Engineering at Purdue University for providing us the resources and also the opportunity to run this course, the School of Electrical and Computer Engineering for hosting this course, faculty who have given us a lot of advice and opinion of how to run this course properly. I want to give special thanks to the two TAs, Guangzhi and also Tolonai, who have been working extremely hard for this course to grade the exams, to grade the homeworks, and also designing the homework problems. There are also a bunch of supporting staff, including our secretaries and also other people who are involved in this course. I also want to give a special thanks to everyone who is watching this video. Thanks for bearing us during this COVID-19 outbreak. I know that we should have been doing the in-class discussion of a lot of these technical topics. However, we are not able to do so. So thanks for bearing with us by just watching the video and providing us the feedback. This is really our first time recording the video in a studio and also in my home. And so if it looks not good, please give us a smile. We will try to do better in the future. Now, your continuous support is really, really important, and therefore I kindly ask everyone to take your time to do the course evaluation to give us some constructive feedback. So thank you very much for taking the course. I hope to see you again in the future. If you have any questions, feel free to email us. If you have any research problems that you want to discuss, also feel free to email me and other teaching staff of this course. Thank you very much.